Hi, good morning, folks. Welcome to our lesson on 7.2, partial derivatives. And so this will be the very last section that is on our first exam. That first exam is coming up in a couple weeks. So check out the La Semana this week for more details on that exam, okay? All right, so 7.2, hopefully a little bit of a review from your Calc 1 classes, but we are here to remind ourselves on how to calculate partial derivative and to use those partial derivatives in a few different ways. And we're also going to take a look at finding second partials, okay? So let's get started. All right, so a partial derivative is something we do when we have multivariable functions, okay? And so what I mean by that is over here, we've got z is f of xy, so we have two different inputs. So we have two input values. And so when we have more than one input value, we just call that a multivariable function. And the more variables there are, the more partial derivatives we can take. So when we take a partial derivative with respect to x, then we are treating y like a constant, okay? Let me highlight some of that. If we're finding a partial derivative with respect to x, then we are treating y as a constant and x as the only variable. On the flip side, if we have a partial derivative of f with respect to y, we're treating y as the only variable and x as a constant, okay? So it is really important that when we're writing things, we're careful, but when we're reading problems too, we're thinking about like what it is that we're finding, okay? Now, geometrically, what this means is a partial derivative with respect to x. Well, all that tells us is the slope in sort of the x-axis direction, okay? So we're still talking about slope, but a partial derivative with respect to x gives you the slope parallel to the x-axis. And then similarly, the partial derivative with respect to y gives the slope in sort of the y direction, okay? Now, there's a few different ways to write this, and so I want to make sure we're clear with all of them, okay? Now, most of the time in class, I'm going to be using this like f with a little x, all right? This is my favorite notation because I think it's very clear to say I'm taking a partial derivative with respect to x. But there is the Leibniz notation, and sometimes you might see that as df or partial f partial x or partial z partial x, okay? Now this symbol in front, it is not a d, all right? It's called partial. So this is partial. And we write it kind of like a 2 with a big fat bubble on the bottom. So kind of like this, right? But those symbols are important to use when we're saying we're taking a partial derivative, okay? All right, so hopefully we've seen this before, but let's jump right in. Let's review on how we take derivatives, because I know we've been focusing on integrals for kind of a long time now, okay? All right, so example 1 says find partial f partial x and partial f partial y for this multivariable function f of x equals 2x squared minus 3x squared y plus 5x plus 1. Okay, so let's go ahead and find our partial f partial x first, okay? Now, all we're going to do is we're going to take our equation, and everywhere we see an x, we're going to treat that like a variable. And then all of the y's we're going to assume are like constants, okay? So let's start with our 2x squared. That's going to be 2 times 2x to the 2 minus 1. So I'm going to use my power rule there. minus 3y, because those are both constants in that second term, times 2x to the 2 minus 1, plus 5y is all considered a constant when we're looking with respect to x. So that's going to be 0. And then the derivative of 1 is also going to be 0. So when we're treating x like a variable, 5x plus y, that whole thing we really treat as a constant, okay? So if we were to clean this up, we could say partial f partial x equals 4x minus 6xy. And I get the 6 from the 3 times 2. So we like to clump all of our constants together. We usually go in alphabetical order, and we have an x and then a y. Okay? Now, this we could also say is our fx, right? That's the other way of saying a partial with respect to x. All right, let's take a look at the partial with respect to y now. So partial f partial y equals, okay, 2x squared. There's no y's in there, so that whole term is considered a constant. Okay, minus 3x squared, that part is considered a constant, and now the derivative of y is 1, plus the derivative of 5y is 5, plus the derivative of 1 is 0. Okay, so let's go ahead and clean this up a little bit. We'll get partial f partial y equals negative 3x squared plus 5. Okay, so we've done our first example of partial derivatives, hopefully something that we've seen before in our Calc 1 class. But again, we've been doing so many integrals, so let's get back in the habit of using those old integral or old derivative rules. Okay, all right, any questions so far? All right, well, if you do, don't hesitate to interrupt. Let's take a look at example 2 over here. Okay, so now I'm using the other notation. I'm saying fx and fy. Those mean the same thing as partial f partial x and partial f partial y. I chose one that had an exponential because I do want us to remember how we do our exponentials, but also one of my favorite rules, which is chain rule. Okay, so fx equals the derivative of e to the x squared plus y squared. So e to the x squared plus y squared, because derivative of e to the x is e to the x, but we need to remember this is not just x up here, so we need to take a derivative of the inner function. And derivative of x squared is 2x, but the derivative of y squared with respect to x is 0. Okay, so let's clean this up a little bit. We get fx equals 2x e to the x squared plus y squared. Okay. All right, let's do the same thing with our partial y or fy. Now, the outer function is still e to some power, so my first derivative is e to the x squared plus y squared times, all right, now we're taking a derivative with respect to y, so x squared is actually a constant, plus the derivative of y squared is 2y. Now let's put those all together. Fy equals 2y e to the x squared plus y squared. Okay, so they look almost similar, but you can tell where we're treating one letter as a variable and where we're treating one letter as a constant. Okay, all right, let's move along. Let's take a look at example number 3 here. And let's take our first partials here, right? This will be our last example where we only take our first partials. So I look at this and I'm like, oh, I see that I have an inner function. That's not how you spell inner. You have an inner function and you have an outer function. And so just like you may have discovered that I have this secret love for U substitution, I similarly have a secret love for chain rule, okay? So let's find our fx. All right, derivative of the outer function first. 5 times, keep the inside the same, to the 5 minus 1 power, or 4 power, times the derivative of the inside, but we're only treating x like a variable. So derivative of x squared is 2x, plus the derivative of 2xy is 2y, right? Now, we could clean this up a little bit. We can say fx equals 5 times 2x plus 2y times x squared plus 2xy to the 4th. That is more the classic way to do it, where we move terms that have the smaller powers to the front. All right, let's go ahead and find our fy. We're going to start with the same outer function, right? It's both something to the 5th power. So 5 times x squared plus 2xy to the 4th times, all right, x squared, when I'm taking a derivative with respect to y, is actually 0. And then 2xy, when I take a derivative with respect to y, is actually 2x. Okay? And so in this case, I think there's a little bit more to clean up. We could take 5 times the 2x and make that a 10x times x squared plus 2xy to the 4th. Okay? So they look similar, right? That last bit looks similar, but the front part, that like chain rule inner function derivative, that's where we really see that partial x, partial y come into play. All right, before we move on, any questions about first partials, or give me a thumbs up if you're feeling pretty good about those. All right, sounds good. All right, let's take a look at what we have next then. Okay, so second order partial derivative, okay? Just like we can take a first derivative and a second derivative, we can take a first partial and then a second partial, okay? Now, when we talk about partials, if we have 2 first derivatives, we actually have 4 second partials, okay? What I mean by that is from fx, okay? It's not a lot of room, sorry about that, but from fx, we can take another derivative with respect to x. We call that fxx, okay? So it's like we take a second derivative and we treat x like a variable again. But if we use the Leibniz notation, that might look like this: partial squared f over partial x squared. Okay, now I am going to be using this notation like 99% of the time, but a lot of the textbooks and resources online do use the partial notation, so I want you to be able to read both of those, okay? But the reason why I like the fxx is because we literally read from left to right. Like we do with respect to x first, and then we do with respect to x second, okay? But if we start with our fx, we can also do fx and then y. And that means we take a first partial with respect to x and then a second partial with respect to y, okay? Now, the way we write that in the Leibniz notation is we say partial squared f over partial y partial x. And so we almost read this one backwards. All right, that's really the main difference. But that's why I find that like using this notation is just a little bit easier to understand what you're doing, okay? So be prepared to read both, but know that in our notes, we're mostly going to be using the fx and the fxy stuff, okay? All right, so on the flip side, what if we took our first partial and it was fx or fy, right? Our second partial could be fyy, where we take the partial with respect to f and then the partial with respect to y, and we do that twice, okay? But just like we could sort of switch what we wanted partway through, we could have fy, we find our partial with respect to y, and then we find our partial with respect to x, okay? So again, we read from left to right with this notation. But the way it would look with the Leibniz notation is partial squared f over partial x partial y. So again, with the partial notation, we do have to read it backwards, okay? But the other thing to be really aware of is there's not just 2 second partials, there's 4 second partials. So if I ask you to find all second partials, you better be finding 4 of them, okay? If you only find 2, you've kind of missed part of the point there, all right? So 4 second partials, 2 first partials. All right, so let's go through an example. We're going to go through example 4 where we just find some of them, and this is more to practice reading the notation, but then when we get to example number 5, we're going to find all of them, okay? So here's my function, f of xy equals x cubed y minus 2y to the 4th plus 3. And this Leibniz notation, all right, let's unpack this a little bit. This is saying find the partial with respect to x first, and then find the partial with respect to y, okay? So with the Leibniz, we do have to read backwards. Okay, so let's take this in a couple steps, all right? So step number 1, I'm going to find my partial with respect to x. All right, partial x equals, all right, x cubed y is going to be 3x squared y, because I'm treating y like a constant, minus 0, because 2y to the 4th is a constant, plus 0, because the derivative of 3 is a constant. So really what I have is fx equals 3x squared y, okay? Now, my second partial now is where I want to find the y derivative, okay? So that means I'm treating 3x squared like a constant. So fxy is 3x squared times the derivative of y is just 1, okay? So fxy equals 3x squared, and that is my second partial where I did partial x and then I did partial y. Okay? All right, let's move on to part B. Part B, I think, is a little easier to encode or decode because really I'm finding fyy, right? So I'm doing it once with respect to y and then another time with respect to y. So the order here, it doesn't really matter because it would be the same either way because we have the same letter. All right, so let's find our fy first. Fy is, let's see, x cubed y is just going to become x cubed because the y goes to 1. Minus 8y to the 3rd because y is our variable now, plus the derivative of 3 is still 0 because there's no variables attached. So let's clean that up. Fy equals x cubed minus 8y cubed. And now that we found our Fy, we're going to find our Fyy. Like we're going to find another derivative with respect to y. So Fyy is, oh, how cool is this? X cubed has no y's, so that goes to 0. Minus 8 times 3 is 24, y squared. And let's clean this up. We get Fyy equals negative 24y squared. Okay, so here you got 2 second partials on the same page. So you can take a picture of that if you want. And then we're going to move on and see if we can unpack the other ways of writing, find those second partials. Okay. All right. So we are doing the fxy notation, all right, which means we get to do it in exactly the order we see it. So we are first going to find our fx, and then our second derivative will be with respect to y. All right, so let's find our fx, all right, and fx from above we had was 3x squared y, right? I'm just grabbing that from part A from above. And then second, I'm finding fxy. Oh, okay, so this is actually asking us exactly what part A was asking us, right? So it's so important that we get that order correct. So I can actually write down my final answer from there, which is fxy equals 3x squared. Okay? But the last thing we need to do, sometimes we want to find that slope at a specific point. And in this case, we want to find the slope when x is 2 and y is 3. Okay? So all I'm going to do is I'm going to evaluate now fxy of 2 comma 3. And that means that everywhere I see an x, I'm going to put a 2. And if I saw a y, then I would put a 3. Okay? Quick note on order of operations here. Please don't multiply before you do a power. All right, so we're not doing 3 times 2 gives us 6. That would violate our order of operations. So we got to do the 2 squared first. In other words, we have 3 times 4, which gives us 12. Okay? And all that means is if I find the slope first in the x direction, and then see how that's changing in the y direction, I get 12 at that point 2 comma 3. Okay. All right. We got one last one. Oh, very nice. It's an fxx, same letter, so you don't have to worry about whatever order you're doing it in because the first derivative will be with respect to x, and so will the second derivative. Okay. So let's go ahead. Fx. All right. Fx is the same as the fx I had over there, 3x squared y. Okay. Now I have to find my second partial, and I'm going to treat x like a variable again. So fxx is 6xy. Okay, so I did the power rule with the 3x squared, and I kept the y because y is like the 3. It's like a constant here. All right, last step. Now we're going to evaluate. We're going to say what happens. What is the slope exactly at the point 2 comma 3? So fxx of 2 comma 3 is going to be 6 times 2 times 3. And when we multiply, we just multiply. There's no distribution here, okay? So we don't want to distribute the 6 to the 2 and the 3. This really just says 6 times 2 times 3, even though we have the parentheses there, okay? All right. 6 times 2 is 12, times 3 gives you 36. And that means that the x slope is changing in the x direction at 36 when we're at the point 2 comma 3. Okay. All right. How are we doing so far with our first and second partials? Kind of coming back to us? Excellent. Glad to hear that. Okay. Let's go ahead and find them all. Okay. So these kinds of directions, find all first and second partials. This is where I really want us to know what it's asking, right? We should come up with 2 first partials, and we should come up with 4 second partials. And we could even list them out for ourselves. Like, I better find fx and fy. And then for my second partials, fxx, fyy, and fxy, and fyx. Okay, so all together, I should be finding 6 partials here, 2 first partials and 6 second partials. Okay, now I chose an equation that had a natural log because we haven't seen that one in a while. I also chose one that had a x or a y squared in the denominator because we haven't seen negative powers in a while. Okay, and so before I even start, I'm going to go ahead and rewrite this multivariable function as 3 natural log, well, 3 times natural log x times y to the negative second power. Okay, this is setting us up for if we take a partial with respect to y, we're going to be needing to use our power rule. Okay, all right, so let's find our first partials and go from there. Okay, so fx, we're treating x like a variable now, is going to be 3 times, let's see, derivative of natural log is 1 over x times y to the negative 2 because that's like a constant. Okay, now we can write this as 3 over xy squared, or we could write this as 3 times x to the negative 1 times y to the negative 2. Okay, now the flexibility, being able to go back and forth between these two, are going to be helpful when we find our second partials. Okay, because seeing the power is going to make it a lot easier to find the derivatives. Okay, let's find fy now. So fy is going to be 3 times natural log x, all of the constants stay. And now to find the derivative of y to the negative 2, we use the power rule. Now we have to bring down that power, right? But that's a negative 2 that we're bringing down. So make sure you don't forget that sign. Negative 2 y to the negative 2 minus 1, which is 3 times natural log x times negative 2y to the negative 3. Okay. Now, this is probably the best form for the next step of partials, but I do want us to see this is the same as negative 6 natural log x over y to the third. Okay, so 3 times negative 2 gives us the negative 6 in the numerator. The natural log is also in the numerator. The only thing that moves is this y to the negative 3 because that is the only term that has a negative exponent. Okay, so it's all about whether the exponent is negative, and that tells you whether to move it top bottom. It's not about whether the number is negative. Okay, so like this negative 6, I'm not going to move that because that has a power of 1, positive 1. All right, so we found our first partials. Once we found our first partials, then we can find our fxx, fxy, fyy, and fyx. In other words, we're finding all of our second partials now, okay? All right, I'm gonna make this a little smaller. I don't know why I wrote that one so big, but no, reset. Okay, so now let's find our fxx, okay? So fxx means I start from my fx and I take a derivative with respect to y, or x, okay? So 3 times negative 1x to the negative 1 minus 1 times y to the negative 2, which is going to be the same as negative 3 over x squared y squared. Okay, so again, the terms with the negative exponent, those get moved to the bottom, but like a negative number by itself, that doesn't get moved. Okay, let's find our fxy now. Now that means I don't start here. I don't start from the last one I found. I go back to my fx and now I take a derivative with respect to y. So in other words, I have 3x to the negative 1, and then negative 2y to the negative 2 minus 1. Let's rewrite this. So I get negative 2 times 3 is negative 6 over xy cubed. Okay. All right, I think I did a little bit better on leaving myself space this time, but let me scooch that over a little bit. And let's find our fyy. Fyy means I start from my fy, right? And I want to use the form where I can see the powers. This one, it's nicer to look at, but it's harder to take the derivative of. So when I take that derivative, I get 3 natural log x. All right, power rule time. Negative 2 times negative 3 is a positive 6, y to the negative 4. And I can rewrite that as 18 natural log x over y to the 4th. Okay. All right, now last one here, fyx. That means I'm going back to my fy and I'm taking a derivative with respect to x. And so that's going to give me 3 times 1 over x times negative 2y to the negative 3. And when I clean this up, I might notice something. Negative 6 over xy to the 3rd. Well, that means that our fxy turned out to be the same as our fyx. Kind of cool, okay? Now, for the functions that we are going to be working with, okay, so this is not true all of the time, but when we're looking at continuous functions, meaning there's no weird like skips or jumps or infinite discontinuities, it turns out that your fxy is equal to your fyx, okay? It also means that if you found one, you can find the other one because they're the same, all right? So even though at the beginning I was like, we have 6 partials, right? 2 first partials, 4 second partials. 2 of those second partials are the same. So we really have our fx, our fy, our fxx, our fyy, and then our fxy, which is the same as our fyx. Okay, so kind of cool if you think about that. All right, let's take a look at one last example. All right, so when do we use this, right? We are by trade not super like, physics, chemistry, engineering, math majors. So like, why in the world would we use all these partials? Even if we know how to find them and they might feel kind of fun because it's just pretty procedural, why would we use these? Okay. And so that's really why I want to take a look at example number 6. So it says the productivity of an automobile manufacturing company is given by f of xy equals 50 times the square root of xy, where x represents the units for labor and the y represents the units of capital. Okay. So a lot of times when we try and model things in real life, the input, like the things that change our output, there's usually more than one of them, meaning we are really working with multivariable functions, right? You want to start a business, that depends on a lot of things. It doesn't just depend on one thing. Or you want to get an A in this class, depends on a lot of different factors, right? So this is sort of the use of multivariable functions. But because I know I'm going to be taking derivatives, I want to rewrite this so there's no square roots so that I can actually see what the power is more obviously. Okay. Now, this is the same as saying 50 times xy to the power of 1/2. And more specifically, I can distribute this power here. So I get 50x to the 1/2, y to the 1/2. And now I can see my variables and the powers that go with them. Okay. Now I do want to make a little side note here that if this said 50 times the square root of x plus y, we're just changing one thing, multiplication to addition. We could say this is 50 times x plus y to the 1/2, but that's not equal to taking the square root of each part. Okay, so like the moment we have a plus sign, that actually complicates our lives a little bit. We want to really look for that multiplication so that we can rewrite it this way. All right, so now that we've done that algebra sort of pre-work, let's answer the question. All right, so part A says find fx and fy. So fx equals, keep the constant, power rule, and then keep the constant. And let's clean that up a little bit. We're going to get 50 divided by 2, which is 25. X to the negative 1/2, y to the 1/2. And that's going to give us 25 square root of y over square root of x. Okay. So I want us to make sure that we can like go back and forth between these different versions, because something like this is going to be so much easier to plug in a number, which we're going to have to do in the next one. But something like the first one is going to be easier if we have to continue to take partial derivatives. Okay, so like they both have their strengths, and the way we maximize those is we are able to go back and forth between them so that if we need to take another derivative, we're good. And if we need to evaluate, we're also good. Okay. All right, so let's find our fy. All right. Keep the constant, use the power rule. And this, similarly, 50 divided by 2 is going to give us 25, x to the 1/2, y to the negative 1/2. And if we rewrite this carefully, we have 25 square root of x on the top and square root of x on the bottom. Okay. All right. We got our fx, we got our fy. Now let's plug in some numbers and see what this is telling us. Okay. All right. So part B says, if the company is now using 250 units of labor. Okay, so I'm going to get my highlighter back for a moment. 250 units of labor. Now, labor was the blue, so I'm going to, was the X, so I'm going to color code those the same. And then 125 units of capital, and we said the capital is the Y, so I'm going to color code those the same. All right. So the company is now using 250 units of labor, 125 units of capital. Find the marginal productivity of labor and the marginal productivity of capital. Okay. Now, the productivity is like, how efficiently are you working? Okay. But when we talk about marginal productivity, we're like, well, if we added more labor or more capital, would that really help? If we put more money into something or we hired more people to do stuff, would that actually make our productivity go up? Or would we actually become less efficient? That's what this is really telling us. Okay. All right. So the marginal productivity, so we'll call that MP, marginal productivity of labor. All right, so we do like the little sub X. This is really saying find Fx at 250 for X and 125 for Y. Okay, so when we're looking for marginal productivity of labor, we're taking our partial with respect to X because X is labor, and then we're plugging in the points that we have. All right, we're plugging in points, so I'm going to use the version that I blocked off earlier. 25 times the square root of 125 over the square root of 250. And because we're looking to find like the actual marginal productivity, we're going to throw this into a calculator. We get 17.68. Okay. What that means is with 250 units of labor and 125 units of capital, if we add a little bit more labor, we're actually going to increase our productivity a little bit. So that's good. If we got a negative number, then we would be like, ooh, that productivity is going down if we add more labor. Okay. Now, similarly, the marginal productivity of capital, marginal productivity of capital is asking you to find Fy at the values that you want. So because I'm evaluating, thank goodness I rewrote it earlier, I'm going to grab that version and I'm going to get 25 square root of 250 over square root of 125. And when I throw that into the calculator, I get 35.36. And so what this means is if I am working with 250 units of labor and 125 units of capital, and I add a little bit more money, like I put a little bit more money into this car manufacturing business, the productivity is going to go up. Okay. In fact, we could see like, should we add more labor or should we add more capital? If we add more capital, we're going to get more productivity. So like at this point, it's really important we put more money, more capital into the business and focus less on increasing the labor. Okay. Now, if this was a negative 35, we would say, oh, we don't want to add more money because that's actually causing our productivity to go down. Okay. All right, so let me get this all on one page for you, the last example. But that's all we have for today. So I'm going to go ahead and stop our recording.